All right, so conductors contain free chargers, or free charges are like electrons, right? That's how we think about it. As an electron has a negative charge, it flows freely. When an excess charge is placed on a conductor, or the conductor is put into an electrostatic field, charges in the conductor quickly respond to reach a steady state, or what we call an electrostatic equilibrium. So everything in the universe prefers to be in a state of equilibrium. Okay, will somebody get that for me, please? So this equilibrium, there are a lot of moving parts to be in a state of equilibrium, but basically I'm going to this is not the definition of electrostatic equilibrium, but this relates to electricity. So think of a battery. When we charge the battery, what happens is we force all the electrons, these are negative charges over here. And then when we do that, we polarize it, we have a positive charge here. Now this will cause a voltage potential. So the battery is charged in such a way that all of the negative charges are on one side and all the positive charges, well, it's positive because there's an absence of electrons. So over here, these positive, you have an overall positive charge because you're missing electrons. They're not missing, they're just far away. And so when I close the loop, if I take a wire and then I put a light bulb, that is a perfectly drawn light bulb. Oh no, that's not bad. I think you guys are gonna not learn this concept if I leave that as your light bulb. We'll do this. There we go, that's better. And I connect my light bulb right here. A basic circuit is just closing the loop. So I have the potential, all these electrons want to reach a state of equilibrium. All these positive charges need electrons. So when I close the circuit, what happens is I create a path for those electrons to move. So what'll happen is I'll have an electron that will leave this side and go through the circuit, and as it leaves that side, it'll do some sort of work, light a light bulb and a bunch of other stuff, and then move through over here, and then until it's balanced. And then once all the electrons move over to this side, we have to recharge the battery. Does that make sense? Now that's a state of equilibrium. That's where it wants to be, sort of, but there's other parts that also want to be in a state of equilibrium. So let me show you this diagram here. So for part A, when an electric field E, capital E, is applied to a conductor, free charges inside the conductor move until the field is perpendicular to its surface. Okay. The electric field is a vector quantity with both parallel and perpendicular components. This is going to be important because we're going to connect the dots with this to magnetism. Okay? The two go hand in hand. All right? So the parallel component of the electric field exerts a force. This force on the charge, which moves, so when you think about this, this will have a charge, and that charge is equal to the charge of an electron times the magnitude of the parallel energy or electric field. Okay. And so this could be a positive charge or a negative charge. In this particular one, they say a positive charge, which is interesting because electrons move, but we always call it a positive charge, right? So we'll wait till we get to some examples of that. But the parallel component exerts a force on the free charge, which moves the charge until this equals, so this happens until F parallel approaches 0. You guys know that when I write it this way that this little arrow means approaches? Okay, just double check it. So it doesn't start off as 0, but what happens? Well, as we move those free charges, whether they be positive or negative, depending on how you want to look at it, eventually we're done moving, and when we do that, the resultant field is perpendicular to the surface of the conductor, right? And so then the free charge has been brought to the surface of the conductor, leaving everything in some sort of electrostatic equilibrium. Okay, so you could think of it like this. The positive charge is here. There is an electric field, and this arc represents like the conductor. So just think of like a circle, like a wire. And so as the electrons flow through, there's this dynamic where there is a force, and that force causes the charges to move. The electric field is a resultant vector of both the perpendicular, the surface, right? And then there is an electric field that runs parallel to the force. And this is going all around the conductor. Does that make sense so far? So then the conductor, do you have a question?
So E stands for electric field?
Yes, this is electric field. So this is the electric field, right? And then this is the components of it. So this component mathematically generates the force, and it's perpendicular to the surface. So think in terms of calculus, this would be what we call the tangent line. And then this would be perpendicular but going outward. So it's kind of like the radius. Does that make sense? Okay. It looks more like this. And so then that generates an electric field. So the a conductor placed in an electric field will be polarized. So it's interesting. A conductor what they're saying is when you have a conductor and electrons flow through it, it generates an electric field. If you just have a conductor with no flowing electrons and you place it into an electric field, it can polarize the actual conductor, which will make sense after I explain some more stuff. So the result of placing a neutral conductor, no free charges flowing, into a uniform electric field, the field becomes stronger near the conductor, and then it disappears inside. So here's another image. So think of it like this. This is an electric field, right? And then this image right here is the conductor. Whoops. This is how generators work. Because you can have an electric field and a magnetic field. They're like opposite sides of the coin. In fact, electromagnetic radiation, or you guys often refer to it as light, propagates. And as it propagates through space and time, you have the electric field and the magnetic field. They're orthogonal to each other, which probably doesn't make any sense to you now, but I'll explain it more. So the illustration that I got there on the screen shows that a spherical conductor, we're talking about the cross-sectional, yes?
So for the negative and the positive, would it be a negative electron and positive electron, or is the negative?
This is the polarization of the charges. So in order to get a mostly negative charge on one side, the free electrons would have to move to one side. When they move to one side, they leave, because they're moving away from protons, that leaves a slightly more positive charge
So
on the other side.
Plus is a proton then, not a positive electron.
It is an excess of a proton in the absence of electron. So remember, this is what I'm talking about. So like, if you think of an atom, a regular atom, it doesn't matter what the metal is, it could be copper, right? So, let's look this up real quick. Maybe this will help. Oh, great. Of course, the internet's slow. Crap, where is it?
It's 29.
Oh, yeah, there it is. So copper is a pretty good conductor for electricity. So one of the reasons it's a good conductor for electricity, the valence electron, it has one electron in the outer energy field. So that's free moving. But also, it's supposed to have 29 protons, which means that if you add all this up, it has 29 electrons. So what happens in this image here is those electrons and the valence electrons, some of them will be polarized and they'll gravitate. In other words, over here you have copper atoms that have 30 electrons. And over here you have copper atoms, not all of them, but some of them, especially those closest to the surface where it has the highest interaction with the electric field. Those will have, 28 electrons. Yes?
It's like metallic bonding the sea of electrons.
Kind of, but it's not a bond. It's temporary, and it's very dynamic. So they don't want that ever. They don't want it. So when the electron, when that one electron jumps ship and goes to, because it's being drawn because of the interaction of the electric field, it doesn't like it, so it wants to go back. And so there's always this constant exchange. It's not a permanent thing, it's more dynamic. And when one goes back, the electric field is constantly drawing it. Think of a magnet and metal, right? So if I have a magnet and I have metal, it's going to pull the metal towards the magnet constantly. It's a similar thing, except the electric field is actually pulling on the electron to kind of move it over. Does that help? Okay. And then also the electric field, because of this interaction, it actually causes the electric field to change its course and move closer to the conductor. So this just happens. So then there are a couple of misconceptions about the electric field inside the conductor. Because if you have an electron moving, it generates a field. And if you have an electric field, it can cause movement of an electron. So a generator works because you have a magnet that moves around inside another magnet, and that magnetic field actually is like having stuff inside of, it's like having a conductor inside of an electric field, and it causes those electrons to move, okay? A motor does the opposite in the sense that it uses the electrons and the charges to force objects that will move to actually move. But they're the same thing. It's just it's like two sides of the same coin. One side is magnetic, the other side is electric. And so each excess charge is placed on a spherical conductor, repel and move until they are evenly distributed. So excess charge is forced to the surface until the field inside the conductor is zero. Outside the conductor, the field is exactly the same as the conductor as if it were placed by a point charge in its center. So anytime we do fields, and let me write that down because it'll be important. Anytime we do fields, so at some point you guys will learn about gravitational fields, magnetic fields, but fields, we focus on the center. So when we talk about gravitational fields, we can do all the math based on the center of mass of the object that we're focusing on. Same thing with charges. Same thing with electric fields, magnetic fields. Yes?
So that means we'd also have to use the radius then for our formula?
Sometimes, yeah. That's why when you remember the gravity formula, where it's the gravitational constant G times m1 times m2 all over r squared. The reason we're using r squared is because it's a spherical. The fields are always, and at some point you use calculus to determine what is the strength of the field. The field, as you go further away, won't be as strong, right? And it'll, you know, based on that, the inverse square proportionality. Okay, and so I'll give you a second to sketch that out. But the outside of the conductor, the field is exactly the same as if it is the conductor were placed by a center charge. So it's within the conductor, it's the same as the center. Okay. Now, the mutual repulsion of excess positive charges on the spherical conductor distributes them evenly on its surface, and so the resulting electric field is perpendicular to the surface and zero inside. Outside the conductor, the field is identical, that the point charge in the center is equal to the excess charge. So it's no accident that this proton, when you think about this proton here, and it's not really a proton, it's the absence of an electron, but this positive charge here won't go next to this one, and it won't go next. So this one is pushing this one this way, and this one is pushing this. So this almost has to be centered between these two positive charges on the surface. And they also push away from each other, right? So these won't get real close to the center, so there's this thing where it's, and so it's evenly distributed around the outside of the conductor, not towards the surface of the conductor is how I should word that. But the outside of the conductor, the field is identical to that of the point charge in the center. So if we were to measure a point charge right on the surface of this, it'd be the same as the center. Does that make sense? So I'm gonna write down some properties, and I want you guys to copy this down because this definition is important. So the properties of a conductor in electrostatic equilibrium, the electric field is zero inside the conductor. Just outside the conductor, the electric field lines are perpendicular to its surface, ending or beginning on the charges on the surface. Any excess charges reside entirely on the surface or surfaces of the conductor. Okay, you almost done? Okay. So a lot of modern day electronics start with conductors and this concept of electric fields and charges and how to manipulate these charges. Your guys' smartphones use binary. A 1 has a charge, a 0 does not have a charge. So everything your smartphone does is some sort of calculation that's in binary, and we zap it or we don't zap it. I'm really simplifying it, but this is how it works. So if I take 2 plates, this is how you can create a uniform electric field. However, the uniformity of this is more consistent right here on the inside of it. I don't know what happened, why I have that there. So this is a very uniform electric field. Now you may have noticed that over here on the outskirts we got some wonkiness. That's the official physics term. We got some wonkiness here, and we got some wonkiness here. Do you guys know why that wonkiness works, or where it comes from?
The edge.
It is on the edge, but why, if you were to guess? There's no additional plus charge or negative charge. So these are uniform because they can't get real close together, and it's almost like Ghostbusters, you can't cross the streams. Okay, so on the edges we don't have these extra charges, and so because they're absent, you know, the field is just going to go wherever it wants. Now this is how the old school picture tube TVs, which we call CRTs, this is kind of how they worked. So we would call it this, I'll write down picture tube TVs. This was a major component in a picture tube TV. It's really simplified. So the first televisions kind of took advantage of this uniform electric field. Essentially they would hit this cathode ray tube with charged particles, and then the tube would interact with those charged particles, and at first it was just black and white. So really white things were a high charge and it would be light. When they got to color TV, what they did is they did a frequency. So the frequency response corresponds inversely to the wavelength, and the wavelength is the color that you see. LED TVs do a very similar thing by producing the light. They just have a lot of those LEDs. LEDs are safer for humans, right? Because the light is on the surface of the LED, and all the interactions are in between the LED. And have all of you guys, I know you've seen like LED strips. Have you guys taken a look at LED strips up close? A lot of this goes inside the LED, and then you're only bombarded with the light. The old school TVs, the charged particles would pass through the picture tube and hit your body, almost like, well, it's radiation. It's a form of radiation. So we got. I mean, they just kind of got rid of them. So they said they were safe, but you know, who really knows? So, anyways, can I move on a little bit? So when I'm going to put an image up here. Earth is a conductor to some degree. And this is how we get lightning sometimes. So lightning is nothing more than an electric field between two charges, right? The Earth is a ground, and that field, as it goes through matter, do you guys know how light bulbs work, since we're talking about it? So what happens is, a very simple explanation of a light bulb is that you have an electron that has a negative charge, and then you have this nucleus down here. And this thing's going around this thing, right? Now, for whatever reason, this is a state of equilibrium. For whatever reason, if I zap this with electricity and I put an extra charge on this, then this might increase to a higher energy state. So because this distance from, we got a proton in the middle here somewhere that's balancing that electron, it doesn't like to be that far away. So it has to give off some energy, right? And I shouldn't have used a proton. I should have, so what it does is, in order for it to come back down to its state of equilibrium, it needs to give off light. So it gives off light. And so there are a variety of things that take place. But lightning, as this charge or electric field comes and connects with Earth, it's charging the particles of air. The particles of air are absorbing those extra electrons as they come through. Usually it happens when it's raining because the moisture in the air provides the path. It's like the short circuit. And then as it moves through the air molecules in the air, those electrons in the air molecules charge up real quick, and then they dissipate that energy. Does that make sense? Do you have a question?
So the lightning makes the light from the electrons that are in the air already?
Yeah, so what's really going on, no. What's really going on, there are times where you have this buildup, a separation of positive and negative charges. But it doesn't mean that the electric field, because it doesn't have a path, doesn't go through. Does that make sense? Or you could have an electric field that causes the charging. So it's hard to explain without, the explanation might confuse you more. So I'm going to try to keep it simple today. Does that help?
Yeah.
I'm going to teach you some other stuff, and then we'll come back and look at it. Okay? So then, in the case of the Earth, if the electric field, and so let's write this down. It is uniformed on the Earth, so I'm going to write some of this down, and it's right in the textbook, but it is about 150. Remember, it's a force. The electric field has a relationship to the force based on the charge, and it's directed down. And surrounds the Earth with a magnitude slightly higher as we get closer to the surface. What causes the electric field? Well, at around 100 kilometers from the surface. Well, let me draw Earth. I don't want to draw Earth. I haven't been doing so good with my drawings lately. Oh, there it is right here. Perfect. So we have this coming down toward, let me put the Earth right there so you can kind of see it. So at about 100 kilometers, so let me add some additional information here. At about 100 kilometers, we have charged particles, okay? And that's called the ion sphere, right? Remember, ion is an atom or a molecule that has a charge because it does not have the same number of electrons as it does protons. So it has a slight positive or negative charge. Ions exist in the world. If I take 100 molecules of anything in creation, they balance out, but some will have a slightly negative charge, some will have a positive charge. Lithium ion battery is based on an ionic. It's an ion that can accept the electron. So the lithium ion actually is the electron transport to carry the electron to the other side of the battery. So remember earlier when I said that you have to move all the electrons over? Well, how do they get over there? Yeah, the lithium ion actually has a hole or opening for that negatively charged electron, and then it'll slide over when you charge it. Does that help at all? So then in the ionosphere, I can never say that word, there's an electric field surrounding the Earth. In fair weather, it's positive, okay? But the Earth is mostly negative. So you could think of it like this. The Earth has like a bunch of negative charges because it's a ground. Whoops. So on the surface of the Earth, you have all these negative charges, right? Because it's a ground. That's why, and I told you guys this, and you'll learn this when you start to learn about electricity. Everything that has electricity has a wire that goes into the Earth. There's some sort of metal conductor that goes into the Earth because the Earth is, for the most part, on the surface negative. Okay? Now in the ionosphere, guess what we have? We have positive charges. And by nature, they're kind of distributed. And I'm not going to draw them around the entire Earth, but just know that they go completely around the Earth. And in fair weather, they don't do a whole lot. And there's a reason why this happens or this occurs. And we don't need to know that today. It just is. This is a natural phenomenon. Okay. But during a storm, the clouds form and the electric fields can become larger. They can reverse in direction. And the charge distributions depend on local conditions. Okay? If the electric field is sufficiently large, the insulating properties of the material break down and they become conducting. For air, this occurs. So air conducts around okay. And so what they're saying is, for the most part, these are kind of balanced out, but if you have weather conditions, you can kind of force a group of these together. And so that's going to kind of create the potential for you to have lightning, right? So it'll generate a spark of some sort and you go and you have a lightning strike, okay? Now, electric fields on uneven surfaces are a little bit different. There's some complicated math. So right now we're really going to focus on spherical uniform, because the sphere, remember, these fields radiate, they propagate, they radiate from the center out based on the surface of the material. So irregular fields, and they're not irregular fields. Remember, there's a perpendicular and a parallel component to the surface. So in this case, because it's a perfect circle, it's pretty easy to have uniform electric fields, because the very nature of the symmetry of the circle kind of disperses the charges evenly. And then because it's going out perpendicular to the center of the circle, that's how you get those charges. And if you have two plates, one's positively charged and one's negatively charged, it's the same thing. It's uniformed in the center. But that's not always life. And so I'm going to throw an image up here of an irregular shaped object and how the electric fields and the electric force, how they would react in a variety of ways. So I've got three images here. And so A is really like the forces between the identical pairs of charges at either end of the conductor are identical. So if you look at the magnitude of these forces, the length of this arrow is the same length as this arrow. And then also parallel, which is interesting, to the surface. So this is the tangent line. So F parallel is tangent at this point. And that moves the charges apart until they reach the surface, because they're not going to really leave the conductor. But what they're really trying to say in A is, look, I have a force here, and then I have to have a force that's parallel to the surface. And the reason I call it a tangent line is if you extend that, if you think of that in terms of extending, if you were to pretend that that keeps going this way, that would be a tangent line, which you guys know that would be the gradient or the derivative of that curve. Okay. It's the tangent line. Touches in one spot. Also, but now look at B. So basically what happens? Well, these charges here are going to be farther apart because of the surface, right, and the shape of the conductor. Over here, the conductor is closer together, so obviously these charges will be closer together. And then also there's going to be an interaction over here on the surface, slightly different than the interaction over here. And ironically, if you notice, this has a symmetry across the center, so you can't be guaranteed that, but that's what they're focusing on, wanting you guys to see the difference. Now for part B, so that was part A. For part B, the force parallel is the smallest at the pointed end. And then the charges are left closer together, producing this sort of electric field. So because normally these would be distributed differently, right? The spacing would be uniformed in something that was symmetrical or spherical. But because of the nature of the fact that the electric field that's generated has to be perpendicular to the force that's parallel to the surface, I'm going to have more items closer together over here. So my electric fields are going to look like this. My positive charges are going to be closer together on the narrow side and spread out a little bit on the wider side. And then likewise, if I were to take that same for part C, if I had a neutral conductor, I'm not charging or running free electrons through it, I'm running it through an electric field.
Attention students, bus number 40.
so when I run, these are supposed to be parallel electric field lines, but when they interact with the conductor, they bend in towards the conductor. Notice that the field lines have this weird wonky behavior. Okay. One last thing I want to talk to you about. So we can manipulate this situation any way that we want to get some sort of desired result. So I'm going to put up here. We have a Van de Graaff machine. Maybe I'll bring it in one time where we could do the charges. I just wanted to cover this topic first here. But this is an image. So a Van de Graaff and Faraday cage. So have you guys ever heard of a Faraday cage? You ever seen a movie where there's some guy that doesn't want the government to know his location? And then he's like, he has a chain link fence inside the room of the house where he lives. You guys ever seen that? That's a Faraday cage. So electric fields can cause interference on radio signals like your cell phones and vice versa. So if you create an electric field that, you guys have heard of cell phone jammers and stuff like that, what they're doing is they're creating electric fields that cancel out other electric fields. So anything that's transmitted, any type of radio signal, is going to be electromagnetic radiation. What we see as light is electromagnetic radiation that our lights can interpret and see. But that's a very broad spectrum. So any wireless communication usually operates in that space as well. But if you pump electricity through any type of conductor, it's going to generate an electric field, and that can cause interference. A Faraday cage does a similar thing. So it is really, I don't know. At some point I'll show you how to do it, but consider an image like this, right? So I have a cone. This is how my electric fields would be generated. This is like an antenna at a radio station. The electric field is very strong at the top, and the force it just generates. So lightning rods, like on the top of your house, basically because they have this surplus of positive charges, what they do is they draw lightning to themselves. So let me show you what I mean. So this, I'm talking about a lightning rod on top of your house, and also a transmitter too. So if you just have a conductor like this on the top, and then you have these charges, because you have a conductor like this, it creates a path for those charges to flow. And we just saw that when you have a uniform electric field and there's a neutral, so this is a neutral conductor right here, this lightning rod, uniform electric fields will gravitate towards the lightning rod, and it protects the rest of the house. So lightning rods are usually connected to like some very thick gauge wire that goes to the ground, and so electricity follows the path of least resistance. It's much easier to go through that wire to get to the ground of the earth than go through your house. So these are put on tall buildings to protect them from getting lightning strikes, and they work most of the time. Yes?
So what you're saying is, like, let's say we have a house here and here's the lightning rod.
Yeah.
If lightning came in from, like, here's the rod, it came in from over here, it would drag it that way because of the field?
Yeah, because the field would, remember, the field
Yeah,
gravitates.
Yeah, okay. It's all come together.
Does that make sense?
It does.
And then on the right is a Van de Graaff machine. We have one of those across the hall. Maybe I'll bring it in, we'll plug it in, we'll let you guys' hair stand up. That's always fun to do. It's a similar situation. The Van de Graaff generator, it's a smooth surface that has a large radius, and to prevent the transfer of charge and allowing a large voltage to be generated, it's funny because when you take these apart, there's a rubber thing that goes over a glass thing. It's just like charging a rabbit fur or rubbing a balloon on your head. It just keeps doing it over and over and over. And then those charged particles go on the surface. If you're not touching the earth or grounded, it goes in through your hair like we talked about the other day, and it makes your hair stand up. Okay? That's all the notes for today.
So doesn't that, like, push the electrons to your hair? Or, like,
Yeah,
push them away from each
at
other?
some point